You're watching a Nova Science Now video podcast.
Seems we've done a lot of preparation work to get to this moment of studying the atom in more detail. Atoms are, as we say, the building blocks of all of nature, and we have a scene here of a woman and a dog by the side of a lake. Everything in view is composed of atoms. And how did man, or humans, come to understand the structure of the atom as we know it today? So chapter 4 begins with a historical development of atomic theory, and we'll finish with the quantum model, which is our current working model. But our project for this chapter is to go beyond the quantum model and look at modern research efforts to go into the sub-particles, and that will be really interesting investigation. But let's first look at the path that led us to this point. The man who coined the word atom is Democritus. He was a Greek philosopher, and he had the idea that matter was composed of atoms, which are these indivisible particles. This was right on. This was in the 400 BC time frame. The problem is that Aristotle muddied the water thereafter, and he talked about matter being composed of 4 elements: earth, water, air, and fire. And for 2,000 years, this distorted our view of what comprised matter, until English schoolteacher John Dalton came along, and he came back to the ideas of Democritus that matter is composed of extremely small particles called atoms, and that they are indestructible and indivisible, and that there are different kinds of elements, therefore there are different kinds of atoms, and they combine with each other in whole number ratios to make compounds. 100 years later, English physicist J.J. Thomson came along, and he was looking at cathode ray tubes, which are our old-fashioned television tubes, which is basically a gas in an enclosed glass tube, which they run electricity through it, and they see all these charged particles flowing through, and he's figuring out that inside the atom there are actually smaller particles, and he called them electrons, and he knew they were negatively charged, and he knew that they were tiny relative to the size of the atom. And so he's saying for the atom to be neutral, it must have positive charges in there too, and he came up with what's called the plum pudding model, which is that this pink atom here is positive, but then it's got these little negative floating electrons in it. One of his graduate students, Ernest Rutherford, continues to develop this model. He is the one who is attributed to discovering the nucleus. He hammered out gold into 1 atom thick sheet, and he ran a beam of plus particles, charged particles, called alpha particles, through the gold foil, and most of the time they would pass straight through the gold foil, but sometimes they would ricochet and go off at angles. So through this 2-year study and thoughtful evaluation of results, Ernest Rutherford deduces that there is a positively charged nucleus in the atom. It's really small compared to the volume of the atom. And he also named the particle in the nucleus that's positively charged. He called it the proton. And so this is a blow-up of the idea the nucleus contains the proton, the positively charged proton, and it's surrounded by electrons that are negative, and alpha particles, which are plus particles, pass through the empty space in which resides the electrons and are not deflected, but then when they come close to the nucleus, they veer off at angles, and that accounts for his experimental results. I want to also note before we move on, Ernest Rutherford's work in radiation is also very significant. Next, we want to look at Niels Bohr. He's a very significant scientist from Denmark, and Niels Bohr starts to give definition to the role of the electron in the atom, that electrons can jump energy levels, and there are quantized energy levels or step-like energy locations for the electron within the atom. He looked at spectra of the elements, and he was taken by the idea that every element had a unique line spectrum. If you take an element, and you will do this very experiment, and you put it in a flame and watch the colors that come off, they are unique. Each atom has a unique spectrum of light that comes off of it. And Niels Bohr associated this with the fact that number one, they have different electron locations to begin with, and then these electrons can jump up to higher energy levels when they absorb energy, and when they relax and come back down, they give off light. And so Niels Bohr looked at the unique line spectrum given off by each element, and from that he was able to figure out electron location. He really was only able to figure this out for hydrogen, and his idea of orbits became outdated quickly as we move into the quantum model of today. But we do say that Niels Bohr is the beginning of the quantum model. All right, so just a quick summary of these ideas. First, we had John Dalton say that we had atoms that are indivisible and they're billiard balls. J.J. Thomson, figured out that there are subparticles within the atom called electrons. Rutherford figured out that there's a positive nucleus that's very small relative to the size of the atom. This picture's not really drawn to scale, but he found the nucleus, and he called it the proton in the nucleus. And Niels Bohr gave definition to electron location in terms of orbits, but he knew this was not adequate. So we now need to move into the quantum model, which is our current working model, and we'll look at this lineup of scientists. Niels Bohr knew that the electrons are in quantized energy levels, but that was hard to understand. Louis de Broglie comes along and he says, if we consider the electron as waves, then there are certain harmonic oscillations of waves that will work, which will help account for why there are these step-like energy levels called quanta. And then Werner Heisenberg is attributed with the uncertainty principle, and he's saying, let's not look for specific orbits, but let's instead look at probability regions. So we come up with like these cloud ideas. And so here is this picture of the atom, and we have spherical shapes, and we have these dumbbell shapes, and these become the probability regions for the existence of the electrons. And Erwin Schrödinger is the mathematician who develops quantum mechanics to create these probability regions mathematically, and we come up with the names of 1s, 2s, 2p, all of these cloud-like regions in which the electrons can exist, and they also have energy definitions with them. So this is the quantum model. We do have a positive nucleus way down deep into the atom, and then the electrons exist in these cloud-like regions that are keep them away from each other because they're all negative and they repel each other, and it helps space them out as far apart as possible. And there are all sorts of orbital shapes, and we look at this in Chapter 9, but we focus a lot on electrons because electrons are where bonding occurs between atoms, and they actually merge these clouds, these orbitals, and become joint clouds, or else transfer electrons, and this is how we make molecules. To wrap up this video, I want you to gain a sense for the relative size and charges on the subatomic particles of protons, neutrons, and electrons. Protons and neutrons have similar masses. They are inside of the nucleus, and I didn't even mention James Chadwick discovered the neutron, which helped account for the rest of the mass of the atom. That was actually difficult work, and it came after the work of Bohr because of it having no charge. It was neutral. Okay, so we see that the mass of the proton and neutron is 10 to the minus 27 kilograms. The mass of a proton is 1 AMU. What's an AMU worth? 1.67 times 10 to the minus 27 kilograms. But that's a very inconvenient number, so we call it an AMU. So we literally count up numbers of protons and neutrons to establish the mass of an atom. But the electron is much lighter. It's 1,800 times lighter than a proton and neutron. So we do not count electrons when we're figuring out the mass. We just count protons and neutrons. We'll practice this more in the next video. And now let's get charges straight. The proton is positive, the neutron is neutral, the electron is negative. Within an atom, we have equal numbers of protons and electrons to make it neutral. Elements are defined by their numbers of protons. The proton count is the identity of the atom. That is called its atomic number. It's given the symbol Z. A helium atom always contains 2 protons. That's what defines it as helium. An aluminum atom always contains 13 protons. Z equals 13 for aluminum. The periodic table is organized by atomic number. We say there are approximately 100 types of elements or atoms known to man. They are laid out sequentially. 1. Hydrogen. 2. Helium. 3. Lithium. 4. Beryllium. 5. Boron. I asked you to memorize 1 through 54 and then a smattering of other elements. As we go left to right, we're increasing proton count by 1 each time. The electron count also increases by 1 because every one of these atoms is neutral. However, the neutron count is not a definite increase by 1. Neutron count can vary from atom to atom. We'll talk about that more in the next video. To wrap up, I'd like to look at this YouTube video, which is a good summary of the historical development of atomic theory.
Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton did experiments and said, I think it's clear atoms are tiny indestructible spheres. Thomson worked with cathode rays, said I disagree. A plum pudding model makes much more sense to me. A new chapter in atomic theory started to unfold when Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked them off the track. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg, and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Bohr saw spectral lines for hydrogen and said, it seems to me electrons move in orbits with specific energies. Heisenberg said, forget it, there's no way to know the orbit or a path where the electron's gonna go. Schrodinger used lots and lots of fancy mathematics. It made a model of the atom based on quantum mechanics. It has orbitals, and those are based on probability. The atom is a fuzzy blob of pure uncertainty. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place.